Our goal for today is to show that ATM is not inside of sigma 0. Now let's expand what these mean. So ATM, X is inside of ATM if and only if X is equal to the encoding of M and W, where M is a Turing machine and W is inside of the language of that Turing machine. Sigma 0 is all languages that are described by a decider. And remember, what a decider is a Turing machine that never loops. It always says yes or no. All right? The alternative to this is something inside of sigma 1. Something inside of sigma 1 is something that can say yes, no, or loop. Now remember that this ATM problem takes an M, which is any Turing machine, meaning that it could take a machine that's not inside of sigma 1, it could take a recognizer. So the crucial problem is that this machine right here may loop, but this one over here can't. So the question is, can ATM be implemented in a way that guarantees that it will never loop? Okay, so here's what we'll do to prove this. We're going to do a proof by contradiction. We're going to assume that ATM is inside of sigma 0, and we're going to say that the machine that we're gonna assume that the machine that can run on that is called is solved by machine. Let's call it what's a good letter? How about the letter will be what's a great letter? ATM. We don't want to choose A. That's kind of boring. Maybe we'll have it be run by the machine F. So what that means is that when we run F on the encoding of M and W, it returns except if M accepts W, and it returns reject if M rejects W, or if M loops on W. Okay, that is what it means for ATM to be inside of sigma 0. Now we are going to derive a contradiction, and here's the way we're going to do this. We're going to make a totally new machine, and this machine will be called D. And when we run D, its input is M. All right, and here's what it does. It is going to return except if F of M returns reject, and it's going to return reject if F of M returns accept. Meaning that what D is going to do is it's going to just run F, but you give D the description of a machine, and it runs that machine with the machine itself as the input. Now remember, we already talked about how you can encode Turing machines as binary strings. So we can just take that binary string and just send it into this very same Turing machine. So, like a few classes ago, we took a Turing machine, we wrote it out as a big long string of numbers, okay? So we just take that string and use it as the machine and as the input. And we're just gonna see what happens when you run it. So this would be like taking, my GIF encoder and running it on the GIF encoder program itself. totally feasible to do that, right? Because all the programs on my machine, they just like take files as input, so I could just send them the file that is their own binary. Now, many programs, they would crash and do weird things, but some of them wouldn't. You know what I mean? Like I could take grep, which searches through a file for a string, and I could run it on the grep source code. That like totally works. All right, so that's what we're going to do. So this machine D is totally reasonable. And it is also definitely inside of sigma 0. Why is it inside of sigma 0? Well, we know that we can simulate machines. We can just run them, okay? And if the machine that we're simulating is inside of sigma 0, then we're inside of sigma 0. So all this does is just does the opposite of whatever f does on some particular input. And so since this machine always accepts or rejects, we know that this will always accept or reject. I.e., this one has to have a case. F has to have a case for what happens when M loops, but D doesn't because F will never loop. It will always accept or reject. Now what we're going to do is we're going to ask the question, what happens when you run D on D? When you run D on a description of itself, what do you get? Well, what you get is you get except if f dd returns reject, which you get if D rejects D. So you're going to return except if D rejects D, and you're going to reject if D accepts D. So now we ask the question, what does D of D return? If it returns accept, then that means that it rejects it, which means it was supposed to reject it, which means it was supposed to accept it, which means it was supposed to reject it, which means it was supposed to accept it. So it turns out that this right here cannot return accept or reject. It can't return either of these things. But it has to return something, or, well, it can't really return anything. So since it can't return anything, that means that it must loop. Well, if it must loop, then that means that something inside of the implementation of D loops. Well, we can just look at the implementation of D and we can see that it can't loop, right? The only way it can loop is if F loops. But the only way if F loops is if ATM is not inside of sigma 0. And so this shows that it is not the case that ATM is inside of sigma 0. ATM must not be inside of it. This is an application of what is called the liar's paradox, or the Quine paradox. The liar's paradox is when you write something like, this statement is false. And because English allows statements to talk about themselves, there's this reflective capability. Turing machines happen to have that too because we can encode Turing machines as input, and thus they can talk about themselves. They can simulate themselves. They can look at their encoding. So we can construct things like the liar's paradox with Turing machines. That's exactly what D does. D of D is a statement that says this statement is false. And because we can construct that, that means that we have this nonsensical situation. And so we have now shown that ATM is not inside of sigma 0. I don't know if you find that an exciting conclusion to our story, but we did that. Okay, so next time we'll prove the next thing. So I'll say next time, ... we will prove that ATM not is not inside of sigma 1. Okay, so that's next.